Okay, so what is a fixed point? I already hinted at the answer. A fixed point of a function f is a solution for x in the equation x equals f of x. And in general, fixed points may not exist at all. So if you take f to be the successor function of natural numbers, then you don't have a fixed point. Or there might be several fixed points. Under some conditions on f, we're going to have a unique least fixed point and a unique greatest fixed point. And the one we care about is the least fixed point. It's the one that corresponds better to our intuition of how programs should behave. And you're going to see there's a close connection between what we're doing right now and inductive predicates in lean, because inductive predicates also correspond to least fixed points. And what we're going to look at now is, in some sense, it's the justification for inductive predicates in lean, the reason why they work at all, right? And you might remember there were examples that were, I think, illegal or immoral and so on involving them. Well, it's because they violated the conditions under which a unique least fixed point exists, right? So it's a very interesting theory that is already, in some sense, used to justify, with pen and paper, the inductive mechanism of lean, but now we're going to model it explicitly in lean and use it to define or denotational semantics. So as our first example, consider this equation here, where this is the x, of course, this is the f, which I've written explicitly, and this is the x. Again. And if we beta reduce, then we end up with this term here. So we're saying that x, which is a predicate on natural numbers, yeah, is the predicate such that it is true if n equals 0, or if there exists an m such that n equals m plus 2 and x of m. So what is this mysterious predicate x? Okay, nobody wants to answer. Everybody is shy today. Well, it turns out if you think a bit about it, okay, the predicate is true for 0, and it's true for, a number of the form m plus 2 if the predicate was true for m. So this should ring a bell. This is the even predicate that is being specified here. Or at least even, you could take x to be even and you'd have a solution. I haven't said it's the unique solution. There might be other solutions. Well, actually, it is written here, there's only one solution. It turns out in that particular example, because of the way this is constructed, there's only one solution. And that solution is even. So this equation here fully characterizes even. And if you manage to construct the LFP of this, and you assign that to a predicate called even, it's going to do the job, and you can prove it to be equivalent to even. I'm not going to go into details to explain why this one in particular has only one fixed point, and sometimes you have a different least and greater fixed point. What's more interesting to know is whether whether we are guaranteed to have a unique least fixed point. So whether these conditions, which are hinted at here, are actually met. Right. Here's an example, a trivial one, where the least and greatest fixed points are different. So the least fixed point is the predicate that sends everything to false, and the greatest fixed point is the one that sends everything to true. So this assumes a convention that false is less than true, and that this convention is lifted to function so that lambda, whatever false, is less than lambda, whatever true. And similarly, the empty set is smaller than the universal set. So this makes sense, right? So because sets and predicates are isomorphic, and you want the less than operation to behave the same for both. So this is, all abstract nonsense so far, but we're going to apply these fixed points to semantics of programming languages. And in particular, X is not going to be predicates on natural numbers, but is going to be, binary relations, or you could also use binary predicates if you wanted, that represent relations between states. And F will correspond to, in some sense, the union of either taking one extra iteration of the loop, if the condition is true, or is going to be the identity if it's false. So if I scroll a little bit up, this is what we have here. This is taking one iteration of the loop and then continuing if the condition is true, or it's doing nothing, the identity, if the condition is false. Now, I like it when what's written on the, on the slide, so to speak, or in Markdown, is in sync with what's written above. It's a perfect match. Okay, so another way to look at the least fixed point is to think of it as, it's what happens if you do the loop 0 times, starting with the empty set, or you do it 1 time, or you do it 2 times, and so on. That's the least fixed point of F. So you can build the least fixed point, as a kind of iteration. You iterate, you iterate, you iterate, and then maybe after finally many steps, you hit the fixed point, and then you're happy. And once you've hit the fixed point, you stay in it. Or you keep on going at infinity possibly. That's what the dot says, at least unbounded. That's Kleeni's fixed point theorem. And we see this is, this is going to be the notion that we want. We're only interested in finite number of iterations, right? So either f of 2, or f of 3, or f of 4. Finite number of iterations of the loop. And well, the key observation here, I already stole its thunder. I already said that inductive predicates are closely related here, but they're baked into the logic, so they're taken for granted in some sense, in some axiomatic sense, if you like. We just assume that they work, and somebody worked out the pen and paper proofs to justify them. Whereas here we are explicitly modeling them in the proof assistant, which is a completely different thing. It's the difference between physics and chemistry, if you like.